In this class, we're going to go over the fundamentals of probability, starting with sample spaces and then how we can apply that to some more complicated scenarios, like having multi-stage experiments, using tree diagrams, using probability tables, intersection, union, all those sorts of things. You'll see a chaptered list of everything that we cover in the description. Otherwise, let's get into it. All right, let's make a start. So this one's going to be our second run through of all the probability stuff. So I'm happy to take these at a bit of a faster pace, and if you want me to explain anything in any more detail, be sure to let me know. Otherwise, it'd be probably a bit more effective if we focus the bulk of the lesson on the actual questions. So as far as fundamentals of probability go, we're going to look at sample spaces, we're going to look at how to handle multi-stage experiments, unions, intersections, and then two-way tables, or probability tables. Okay, just make sure I've got all my screen shares up sorted. Yeah, looks good. Cool. Alright, so bare bones basics of sample spaces. The sample space is just all of the possible outcomes for your given experiment. So if I were to roll a 6-sided die, then the possible outcomes I could have would be 1 through 6. Specifically, you would use curly braces for your sample space because curly braces imply that every number in there is a discrete element. There's no interval. Like for example, if I had 1, 6, but if it was square brackets, that would be every number between 1 and 6, which is not what we're dealing with here. We're dealing with discrete possible outcomes. So once you know all the possible outcomes of your given scenario, finding any probability is simply a matter of dividing the outcomes that you care about, the favourable outcomes, by the total number of possible outcomes. So if you wanted to find the probability of rolling a 5 or a 6 on a 6-sided die, 2 of those outcomes are favourable, out of 6 total, 2 out of 6 chance, or 1 out of 3. Whole bunch of different scenarios like that. I can go through some more in more detail if you like. Otherwise we shall move on. Okay. Sometimes you'll have a kind of scenario where the probabilities aren't super discrete as far as I definitely have this or this. In this case, we have probabilities that are proportional to areas. We're trying to throw a dart on some dartboard, and it's assumed to be equally likely to hit anywhere on that dartboard. We want to figure out the probability of landing in the red zone. So if it's equally likely to hit anywhere on that dartboard, then our total sample space is going to be the area of the entire board. So area of the entire board is our rectangle. 20 by 15 is going to give you the area of that rectangle. Then from there, probability of hitting the red means that red is favourable. And so for that reason, we would find the area of the circle, and then that becomes our numerator because that's the favourable outcome. And from there, well, you simplify. Complement probabilities. So the whole idea here is that all the probabilities in a given scenario have to add up to 1. For example, in the coin toss, you either toss a head or a tail, and so both of them being 50-50, they add up to 100%. If you roll a 6-sided die, all the numbers 1 through 6 must be a 1 out of 6 chance because, again, everything in the experiment needs to add up to 1. So what's going on with complement probabilities is that we say that if we know the probability of some event occurring, like let's say rolling a 1 on a 6-sided die is a 1 out of 6 chance, then the probability of everything else occurring is just 1 minus that. So rolling a 1 on a 6-sided die, 1 out of 6, the probability of everything else occurring, other than rolling a 1, that's a 5 out of 6. In fact, I apparently did that by memory. I didn't realize I had this one written up. Nice. Okay, that's sample spaces. Next up, multi-stages. So multi-stage experiments just sort of takes what we did from a simpler version to one where there are events happening in sequence. One of the best ways of handling that is with a tree diagram. So since we've gone through this before, it's worth pointing out that because these are things happening in sequence, the probabilities along each branch are considered conditional probabilities because the only way you can get to that spot on the branch is if you had gone through that previous section. So probability to get to this stage here you had to have hit the event A. That's why this probability is labeled B given A. It's the probability that this event B has happened, given that this event A has happened. That's just a bit of a nuance there.
Chris,
Yep.
if you don't mind me asking, is like the thing on the very last branch between the two like letters A and B? Is that like a different type of union or like what does that like signify?
The thing I'm highlighting now.
The curly thing between A and B, yeah.
Yeah, that's an intersection. So that will cover over here, which is intersection is this bit on the Venn diagram, union is all of this.
Right.
Fair enough?
Yeah.
Sweet.
Thanks.
Yeah, so the intersection. So basically this dot here is event B, this dot here is event A, and so the probability of getting both A and B, that's why that's labeled A intersection B. And same for all of this stuff over here. I realize this diagram doesn't actually have a dot for B, it just says A here, which is interesting. But anyway, so yeah, each of the branches are labeled with a probability. Every split is just another stage. So this is A and not A, this is B and not B, all of those stages. As far as how to use tree diagrams, you multiply along the branches. So if you wanted to get to this spot on the Venn diagram, you would multiply this probability by this probability. Multiply along the branches. If you want to find the probability across multiple sequences of branches, so I want to find this and this, you do this times this, but then you add it to this times this. So you add across the different sequences, but you multiply along the branches. So, basic version of the tree diagram, we toss a coin twice. It's going to be 50-50 no matter what's happening, 50-50 for heads or tails. And so if I want to find the probability of two heads in a row, using this tree diagram, I could say head, head, yeah, head, head, and so 0.5 times 0.5, that's going to get me 0.25. Probabilities across multiple branches, so what am I actually trying to say here? Yeah, so basically, if you start having multiple branches in your scenario, you can look towards the probability itself to try and limit the amount of effort that you're putting into drawing the full tree diagram, because it gets crowded pretty quickly. Like you can imagine, even if we go like here, right? If we're rolling a six-sided die, even twice, right? Even twice, this tree diagram becomes basically impossible to draw, because you'd have 36 different branches, 6 by 6. So one of the things you can do is simply look at the probability you're actually trying to find, and then only draw the parts that actually matter or contribute to that probability. So in this case, we're looking to roll either 3 6s or 3 1s. And so you might start drawing this tree diagram and you'll realize, cool, it's going to be a 1 out of 6 for any given branch here. If I try to repeat that, too much effort. If I only care about 6s and 1s, then instead of drawing everything in between, I'm just going to look at all the branches with 1s, all the branches with 6s. Just be sure to label them accordingly, right? So it's 1 out of 6 for any given branch here. Just because they're not written on these stages doesn't mean they don't still exist. And so you wouldn't write like a probability of 1 here. The reason why all the other branches aren't there is just because we're trying not to waste too much time drawing. With that in mind, it also means that you've done the heavy work ahead of time as far as figuring out what branches you care about. So all 1s would be 1 out of 6 for this one, 1 out of 6 for this one, 1 out of 6 for this one, all multiplied together. Same thing with the 6s there, you add across. Where it gets a bit more useful is where you have different probabilities for branches. This is where each of the statements in your question are dependent on a certain outcome occurring. So for example, this one's all about different meal orders or coffee orders. This one states that if there wasn't a coffee ordered on the previous day, then the next day has a 0.8 chance of ordering a coffee. Whereas on this statement here, it's the opposite. If a coffee was ordered on a previous day, then the coffee on the next day is going to have a 0.5 chance. So it's conditional based on what happened in the previous day. That's where a tree diagram becomes effective. Well, at least most effective, I should say. These kinds of questions, you'll be able to notice them pretty quickly. namely because they're just a big block of text, and so even that alone is usually enough to spot this one out for probability. But that not being the case, you'll be able to spot them by their conditionalities in the question. If they're set up like that, they have to give you a starting point, which in this case is that she starts with having ordered a coffee on that first day. So when we create our tree diagram, day 1 is going to start with a coffee. From there, that means that to finish up the tree diagram, we need to start with the statement that implies that coffee was ordered on the previous day. All right? Coffee was ordered one day, so we know that coffee on the next day is going to be 0.5. That's why this is a 0.5, and the reason why this is a 0.5 is again because all the branches have to add up to 1 in a given sequence. From there, these kinds of experiments, you can always pretty much just duplicate exactly what you just drew on the C branch anyway, because wherever you started, whatever logic you did to set this one up should be the same logic that you used to set this one up, because in both circumstances, they're both starting with C. So those should never be different. What should be different is the M branch, which in this case stood for the meat pie that was ordered. So if a meat pie is ordered, we can assume a coffee was not ordered, because we're told at the beginning she orders either a coffee or a meat pie. That means this statement is going to apply. Coffee was not ordered on the previous day, hence probability of coffee on the next day, 0.8. So our C is going to get a 0.8, and then to make sure everything adds up to 1, that's going to be a 0.2. So pretty much all the effort in solving those kinds of questions is setting up the tree diagram itself. From there, the actual probability that's being asked is almost secondary, really, because once you have your tree diagram, you can find any of these setups that you like. In this case, it was asked to figure out the probability of getting a coffee on that third day. So essentially, we look at our tree diagram, we look at all the spots where coffee existed on that third day, and we try to get to the end of those branches. We can do that from 0.5 times 0.8, and we can do that from 0.5 times 0.5. Two separate branches, two separate outcomes, so they're going to add together. If you find decimal math as difficult, then my recommendation is convert these to fractions. So these would be 1 out of, well, I'll make it even simpler. This will be 5 out of 10, 5 out of 10, and 8 out of 10, respectively. If converting between decimals and fractions is hard for you, definitely go back and actually revise that. This isn't really the time to do that, but being able to convert between decimals and fractions will be very handy for this kind of probability stuff. Okay, cool. Next up. Tree diagrams aren't necessarily always a great idea. Like if you remember from before, the 6-sided die, right? If you roll that twice, 36 different outcomes, very hard to draw that. Sometimes it's better to table things up. So here's that 6-sided die example again. We set up our two-way table by having a row and column be the outcomes of dice 1 and dice 2, respectively. So both numbers 1 through 6 are going to occur on our row and column, and what you put in the cells in between will actually depend on what's actually being asked of you to do, which in this case is find the probability of rolling the same number twice. So that implies the number that was rolled is actually important, so when we put our little cells in here, the little intersections, it's going to be a 1 and a 1 was rolled, or a 1 and a 2 was rolled, so on and so forth. That's what you actually put in there. And then from there you can look and see 6 6s are 36, and then of all of those outcomes, only the diagonal is going to have duplicate rolls. So you're going to have 6 out of 36, or just a 1 out of 6 chance. If you're forward thinking enough, you probably don't have to draw any of this, but this is good for everyone else like me who has to think about it harder. Cool. So again, same example, but this time the thing we're looking for is the addition of numbers. And so under those circumstances, the things that you put in the cells in the middle, those will be the addition of the two numbers that are given. 1 and 1 makes 2, 2 and 1 makes 3. Filling this out doesn't take a whole lot of effort once you see the pattern. And they usually are quite they usually do have a good and easy pattern to quickly bash out. In this case, numbers greater than 8, so that's going to be all 9 and above. They form a nice little triangle there. So number of outcomes was 10 out of a 36 total possibilities. All you do from there is just simplify your fraction up. That's those. Cool. If there's any questions, by the way, at any point, feel free to slow me down. I just know this is probably the second time for a lot of you, so going through it at a bit of a faster pace than otherwise. Cool. Union and intersection. So the intersection, as far as Venn diagrams go, is just where both sets A and B have the exact same elements, right? So it's the crossover between two sets. Whereas the union is just everything that is included in both A and B. Just keep in mind, the union does not actually mean the entire sample space. Just because we've defined events A and B doesn't necessarily mean that is indicative of the entire sample space. There's still this stuff on the outside of your Venn diagram that could also be part of your sample space, which I think I have examples for. Yeah, sure do. So when we get to that, I'll explain that in a bit more detail. Cool. As far as how to calculate a union, you can calculate union by doing the probability of A plus the probability of B and then subtracting the intersection. The reason why we subtract the intersection is because when you add A and B, you actually double up on this intersection bit. So here's what probability of A looks like, here's what probability of B looks like. If you were to add these two areas together, you would double up on that intersection. So we have to take away one copy of that intersection, otherwise we would have too many of them. For what it's worth putting out that the order in which you write the sets in doesn't actually matter, neither for intersection nor for union. That becomes a bit more important when you start handling conditional probabilities, because you'll have like B given A when the thing you're trying to look for is A intersection B. All I need you to understand is that the order those things are written in doesn't actually matter. That becomes important for solving conditional probabilities at a bit of a later date. Okay, so how do you actually identify if you have a union or an intersection? Well, keyword OR pretty much is always going to imply a union. Now I say pretty much always, use your critical thinking skills here. Under these circumstances, it's just when one thing or another thing could be the case. In this case, ace or a heart. So, ace or a heart means find probability of ace plus the probability of a heart, and then subtract one copy of that intersection away. It is assumed knowledge that you have an understanding of the suits and cards in a standard deck of cards. So a standard deck of cards has 52 cards in it, and there are 4 suits in the deck, and so there's going to be 4 copies essentially of any given card, at least any given number rather, which is why we have 4 aces and then 13 hearts. 13 hearts being a quarter of 52. Both of those divided by 52, of course, because you're trying to find the probability of those things occurring. And then intersection just means a card that is both an ace and a heart. In any given deck of cards, there's only going to be one intersection between number and suit. So if you need to revise how a deck of cards works, because I don't know if kids play with card games anymore or not, feel free to revise those, because it is assumed knowledge. Once you have all those terms, plug them all in, simplify. It's just addition and subtraction at that point. Now I do say that kind of offhandedly. Some people really struggle with fraction arithmetic, so kind of like what I was saying before about converting between decimals and fractions, being able to do fraction arithmetic, really important as well. So, in fact, I'll even take a quick pause to show you where to study that sort of stuff. It's under functions and relations, linear, and then review of algebra. So I've got some basics on algebra and then some basics on fraction arithmetic. So if we scroll like all the way down, it goes into specific detail on exactly how you do multiplications, exactly how you do additions in a few key scenarios. So if you need that be sure to have a look at that. Okay, intersection. So intersection is just when both things are true at the same time. We saw that earlier, ace of hearts, right? Both ace and heart. In this example, we're going to look at a pretty common question that comes up a fair bit, which is they'll give you this survey or this group size of a certain thing, and you have to figure out the individual places to place those people in. So we're starting with 50 people, 35 went to either beach or movies or both, so on and so forth. Easiest way to handle these is by working from the most specific information to the least specific information. What I mean by that is start with the intersection, basically. So of the 22 people who went to the beach, 12 also went to the movies. That's very specific. These are people who went to the beach and the movies, hence that's going to be our intersection there. Now, that did come from a total of 22 people, hence 10 remaining would have gone to just the beach but not the movies, right? And that figure itself came from 35 who went to either in anywhere in this Venn diagram, and so from the 22, the remaining 13 must have therefore gone to the movies but not the beach. And lastly, there were 50 people total. Currently there's only 35 in the Venn diagram. This is where you're going to have stuff on the outside of the Venn diagram. So, or at least this is the intersection of M naught and B naught. So this is actually pretty common to have. It's common to have stuff outside of the sample space. And then once you have your Venn diagram, you can answer pretty much anything you want. In this case, it was how many went to the movies but not the beach. That will be this spot here, because it's everything that's included in movies, but it's outside of this circle that is considered beach. So it's going to be 13. Specifically, that is the intersection M, not B. So, movies, not beach. And lastly is probability tables, which excels at solving those intersection kind of questions. That one was, Venn diagrams are pretty good for this sort of stuff. This is more useful for when you have like a bunch of different intersections, or at least one intersection. You can always go from any Venn diagram to a probability table. It almost becomes personal preference which one to use. But okay, how does it work? Well, you basically outline your two events and their complements. So this will be event A, this will be event B, and then the not B and not A. So don't mix and match them. Don't put like A, B here and then A not B not here. They have to stay on their same rows and columns. From there, the intersection of the cells will be the intersection probabilities, and the things that are on the outside will be the total of those columns. So probabilities of A naught, and everything should therefore add up to 1. The way it works is you add either horizontally or vertically, and if you're doing it right, then the two things, like for example, if we did this vertical addition here, this plus this needs to equal this. This plus this needs to equal this. And if we look horizontally, for example, this plus this needs to equal this. So either horizontally to the right or vertically down need to add up together. In the example that I give here, pretty much the first thing you want to do is take all the numerical information and then put them into their spots that exist on the table. So in this case, 65% of people play a sport, so the total of the sport column will be 0.65. 71% choose cardio, so the total of the cardio, C for cardio, column is going to be 0.71. And then lastly, 53% do both. So it's sport and cardio, hence it's going to be the intersection of those two things. To solve any probability table, to complete it, you need to have at least something on the outside and at least one thing on the inside. If you have that, then you can always just do your addition or subtraction to get the terms that you care about. In this case, we want to figure out a probability of cardio but not sport. So here's cardio, here's not sport. We want to find the intersection of those two things. So we care about this spot here. probability tables say that this plus this needs to give this. That's what I've written here. From there, you can just rearrange and then solve for what that probability would be. This is just a bit of a word of warning. Intersections and conditional probabilities are often mistaken for each other. A few key things to watch out for will, these are a few things to consider in the back of your mind to figure out whether what you have is an intersection or a conditional probability. So basically, if the events don't have influence on each other, like if one can happen without the other, then what you're talking about will likely have will be an intersection. Whereas if the scenario that's presented to you can only exist in that context, then it's likely conditional on that context. To give an actual example to it, we have fault rates on assembly lines. So we're told it's an 8% fault rate on line B. That statistic is only relevant because it was a motor that was conditional based on the fact that it came from line B. That makes it a conditional probability. So it's a very tough thing. You've got to just sort of play with a lot of questions to get this really sorted, but these are the two key things I'd be starting to think about, at least initially. I don't know how bulletproof this is, but it's something that I use, and it's reasonably effective at identifying which is what. But otherwise, once you know that, it's, again, just another plug and play. So, oh, I didn't even solve it, yeah. There's nothing else to really talk about there. Cool, alright. That's all the theory around there. If there's anything you'd like me to delve into further, let me know. And if you have any preferences for what questions you want to do, let me know. Otherwise, typically, the toughest kinds of questions up until now could be anywhere from multi-stage experiments or these Venn diagrams. Yeah, let's try at least one of those Venn diagram ones. That way we can be sure of that. So let me see here. This was chapter 9D. Okay, cool. Let me get my phone back on so we can start writing some questions. We'll do the question 4. Yeah, okay. Have a read of question 4 there. I'll start drawing up the Venn diagram, and then someone can let me know how you would handle that. At least just getting things on a Venn diagram. I'll use S for smartphone and C for car. So I guess just as a brief reminder, my recommendation on how to start with it would be start with the most specific information, because that will tell you your intersection. Right, 35 in the middle of S and C. Yeah, that's correct, Peter. Nice. So that 35 in the middle is going to be our intersection. The reason why is because 35 owned smartphones and cars. That's good.
Would that mean only 10 people own cars and 35 people own smartphones?
Yes and no. Yes, in the sense that you've put the right numbers there, but you've described it a little bit inaccurately, which is this isn't the 10 people own cars. This is 10 people own cars, but not smartphones. So it actually also matters to explain what's not included in that spot as well. But otherwise,
Right.
yeah. For everyone else, actually, maybe you explain it. Where do those numbers come from?
So like when you look at the intersection, you can like subtract the intersection from the amount of people who own the specific item,
Hmm.
and then that will give you the amount of people that own it, the probability that someone owns it.
Yeah, yeah, precisely. So there was 45 that own cars, 35 that own both, and so people who own cars but not smartphones, 45 minus 35 gives you 10. Exact same thing for this 70 and 35. That's also going to make 35. Have we finished our Venn diagram though?
There needs to be 20 on the outside because they don't own either smartphone or a car.
Sounds good to me. Yeah, exactly. So again, exact same idea, right? There was 100, and then there were, we figured out everything in the Venn diagram, and so 100 minus that is going to give you what's not in the Venn diagram. Perfect. And then from there, that makes answering the questions pretty trivial. So we'll knock a few of those out and then move on. How many students owned neither a car nor a smartphone? Yeah, 20 people. Nice job, Pia. And then the second one, which was either car or smartphone, but not both. 45. Yep, that was good. You guys are crushing it. Easy. Alright, those are clearly trivial questions. Let's move it back a touch so we can do some of the multi-stage stuff. Let's see what would be any good. So many coin tosses. Is there anything? Yeah, maybe this one actually. I remember these being kind of interesting. So have a read of question 9 and we'll start getting a tree diagram sorted. Specifically, yeah, maybe the first thing we'll do is try to get, yeah, we'll try to get the letters for like the outcomes of our particular Venn diagram going. So I'll let you have a think about that. Let me know how you might start it out. Oh, damn it. I've just realised OBS is bugging out. The recording on this one's going to be very tinny, unfortunately. Damn. Anyway, alright. So, has anyone got any ideas on how we might start this tree diagram? What kinds of things we might start putting on it? Would you start with her entree options? Yeah, that sounds pretty good to me. So, soup or salad. Let's see. How do we do that? I don't know. S-O-S-U, perhaps. Sounds good to me. This one's going to have a fair few things going on, so let's make this nice and wide. S-O-S-U. Wait, why did I say S-U? S-A. S-A for salad, S-O for soup. Yeah, good starting point. Where do we go from there?
Then from the soup and salad, we draw a branch of 3
Yep.
from each. With I use F, C, and S for fish, chicken, and steak.
Yep. F, C, S, F, C, S. Sounds good to me. You might have to double up on C for the cheese, but that's
And
fine.
then from each of the main courses, I drew three more lines.
Mhm.
I for ice cream, L for lemon tart, and then CH for cheese.
Yep. I, L, C, H. And you can imagine I'm just gonna, well actually can I copy this? Maybe that'll make it nicer. Anyway, I'm gonna just copy this a few times. That does set up most of it. While I copy this, have a think about what the probabilities we would start writing out would be. It does pose a bit of an interesting question, which is, if you're not told any probabilities around these things, how do you start labeling them? There is an assumption you'll have to make. It's worth noting that each stage of the tree diagram is effectively, I don't want to use the word independent because it's not quite true, but at least not mathematically speaking, but it's separate, right? So all of these outcomes have to add to give 1, all of these have to give 1, so on and so forth from there. So with that in mind, maybe if we just focused on the first set, what will be the probabilities between SO and SA?
Zero 0.5.
Yeah, 0.5. So when in doubt, you assume everything is equally likely, or at least when you're not told otherwise, you assume everything is equally likely. So yeah, both of those are going to be 0.5s, or I'll just say a half. I personally like to draw an arrow through, just so I don't have to rewrite a whole bunch of probabilities. It's not necessarily mathematically correct syntax, but I think your teacher will understand. Alright, and then the next, well, literally every other branch from there, those are all going to have the same answer, which is
1/3.
1/3s. Yeah, each of them have a 1/3 chance, all the way through, all the way through. we get the point. So all those are going to be 1/3s. Cool. Now, part B, we got to start using it. If Madison chooses all 3 courses and is equally likely, no, I guess we were told it there. Maybe they didn't want us to label them initially. Oh yeah, answers actually don't even have the probabilities labeled. That's interesting. But okay, so now we're assuming it's equally likely. We want to find specific probabilities now. So first one on the block is soup, then fish, then lemon tart. Either I'll grab the actual probability or how we might go about that.
Do we just like multiply down the branches?
Sure do. Yeah,
Like we'll get 1 over 18, I think, if
1
you
over
multiply.
18. Yeah, yeah, that's perfect. So we wanted, what was it specifically? Let's see. It was soup, then fish, then lemon. So soup is a half, fish is a third, and then lemon is a third. The third times a third is 1 over 9, and then halve that down to 1 out of 18. Yeah, slightly different. Chooses fish. So yeah, I won't even say anything else on that one. I'll let you guys think. Probability of choosing fish.
Is it just 1 over 3?
I like that. Yeah, 1 over 3. Now, there's a couple ways you could have done this. Based on your speed, I'm pretty sure I know which method you used. Care to share?
Um, since it doesn't really matter if she chooses soup or salad,
Mm-hmm.
the probability of that is just 1. So then after that, you see what's the probability of her choosing fish, which is 1 over 3.
Yep.
So you just multiply 1 over 3 and 1. So
Mm-hmm. Yeah,
you get
precisely.
1 over 3.
So none of the other courses of food actually mattered. It was just when you got to that stage of choosing fish, did you choose it or not? Yeah, absolutely. Now, if you didn't see that, that's fine. You just would have had a lot more arithmetic to do, which is you want to find every possible outcome that has fish in it. So that would be going down soup, fish, I. I've forgotten what all these things are. Soup, fish, L, soup, fish, cheese, and everything that has fish in it. Lots of math. Obviously not ideal, but at least you do have a failsafe. Triple I is basically the same thing. IV, a little bit different though. Instead of looking at what we want to have, we're looking at what we don't want to have. That's a bit more interesting.
Is it just 2 over 3?
Yes! Nice, another shortcut. Feel free to explain that one.
So once again, whether you go soup, salad, or fish, chicken, and um, fish, chicken, and steak, it
Yep.
doesn't really make a difference. So all those probabilities is 1.
Mm-hmm.
And at the last branch, the probability of you not getting lemon tart is 2 over 3. So you just multiply 2 over 3 with 1, and then you get 2 over 3.
Mm-hmm. Yeah, I think the only thing I'll mention is that it's not necessarily that the probabilities are 1 before it, it's just that you don't consider them at all. You just focus specifically on the part that you actually care about. Because setting them all as probability of 1 is mathematically unsound, but other than that, everything else, like how you handled it, was pretty good. Yeah, cool. So that's IV. Now, part C is an interesting question. I remember getting caught out by this one, so I'm curious to see if you've belt this one out as well. Because if so, I'll be happy to congratulate you. But I remember it being tough. Part C. Can omit a course. So we'll just do CI, right? So there's this change that's going on here. I want to figure out the probability of soup, fish, and lemon tart.
Is this 1 over 54?
1 over 54. Let me double check that. This was CI. No, not 1 over 54. What was your... How did you try to handle the new addition to the experiment?
I just saw what's the chance of her like having the courses, but I think I might have done something wrong with the numbers.
Well, I mean, definitely done something wrong with the numbers, yeah, but conceptually speaking, yeah, I was curious to hear how you handled the.
Yeah, I think I just multiply with 1/3, which is
Oh,
not right.
sure. Yeah, okay. Yeah, you got to somehow put this into your consideration. The fact that you could omit either the entree and or the dessert. That starts mattering. It's a really cheeky way of going about it.
Wait, Chris, just a question.
Mm-hmm.
Is it that like we had the previous possibility of 1/18, right?
We yeah, 1/18.
For having soup, fish, and lemon tart.
Yep.
Since she has to go through all three courses to get soup, fish, and lemon tart, could we just assume that there's a half chance that she will delete one of the courses and then multiply 1/2?
So that would be if you just halve what's going on there. That would assume that the order of choices is entree, main, dessert, omit. Right? When you do multiplication, that's multiplication principle. You're doing things in sequence. So to multiply by half at the end would imply that the choice to omit something is done at the end, and it's a 50-50. Which, not necessarily like couldn't be the case, but what's going on here, it doesn't handle the case where you can choose to omit either the entree and or the dessert. So you've just got a stage at the end which just says omit, which bit vague, doesn't really cover everything that's required here. This one's tough to see. First part, omit the entree. The choice to omit is just in and of itself another choice for your entree. You can have either the soup, the salad, or nothing. That's now 3 choices. And so all we do is we tack on this additional branch onto our tree diagrams for an omit. And so obviously there's going to be all the other shit that comes with it, with all the other branches. The point being, there's now 3 choices for your entree, and there's now 4 choices for your dessert, which the 4th choice being, again, to potentially omit. So effectively all that's happening is now you've got a 1 out of 3s across the board for your entrees, and you've got 1 out of 4s across the board for your desserts. From there, you handle it like you've handled the first version of this question. Clear enough for why we can handle it like that? If so, I'm curious to hear what the answer comes out to.
One over 48.
1/48 is still a bit big there. Should be 1/36. So it should be, what would it be? 1/3 times 1/3 times 1/4. Hang on.
Wait, she can't omit the main course.
Can't omit the main, no.
Oh, never mind then.
Yeah, that's probably why then. So it's either the entree and or the dessert. Yeah. So it does still end up being 1/36, which is if you had halved the 1/18. I don't know if that's just a coincidence or not. I'm pretty sure that's a coincidence. Might have to think harder on that one. Yeah. The point being, this is at least the intended way of thinking about it. So basically, yeah, one out of 3 from the entrees. Mains aren't touched, 1 out of 3, and then 1 out of 4 for the desserts. Multiply all those together, you're going to get your 1/36. Then from there, Yeah, actually, it might be worth touching on to at least double I. Now we can start seeing how this additional option of an omit plays a role. So part double I chooses all three courses.
Is the probability 1 over 2?
It is 1 over 2. Yeah, that's exactly right. Why is that?
You just multiply 2 over 3, which is the probability for her to get to choose a first course.
Mm-hmm.
Second course, there's no omit option, so she has to go through there.
Yep.
Then the third course has a 3 out of 4 probability that she'll eat it. So then you multiply 2 over 3 and 3 over 4
Crushed
to
it.
get 6 over 12.
Yeah, really good done. Really well done. Only choosing 2 courses. Is that even harder at all? Yeah, maybe harder. We'll try triple I.
Is this 1 over 12?
Not 1 over 12. It's a little bit low. Three out of 8. 3 out of 8. Still no. Doesn't simplify down to 3 over 8 anyway. Bit tougher this one here. I don't know if there's a, like, even I'm thinking about it now, I don't think there's a great way to, like, make it a bit higher level, like you were doing, which was simplifying things down. I think you might have to just go through and bash out all the combinations that give you 2 courses. Only 2 courses. I mean, we can maybe think about it like a combination, like a counting methods approach, which is you either have all 3 courses, you have entree main, you have, well, I guess it would be these outcomes, right? So you have entree, main, dessert. You could do entree, main, or you could do main, dessert. Those are the 3 main outcomes, and then it's these that you want, because that's when you have only 2 courses chosen. Have I hit the whole sample space there? You choose an entree, choose a main, choose a dessert. Yeah, that should be the full sample space. And so, presumably, if you find, because finding both of these and then adding it together, probably a bit long, finding this and then subtracting it from total number of outcomes, probably a bit more effective. Because that way it's only one thing you're looking for, which is all the outcomes with entree, main, dessert. Yeah, even that's painful. Because that's that first omit when you do your next... Yeah, okay. Because you can't even really do a counting methods thing either, at least not like super broadly, because this first omit, when you do your next three like mains, you then only have three choices for... Wait, no, it is. Never mind, don't mind what I was just saying there. Because you could do both omitted. Ah, that's what's the issue, yeah. So I was doing a counting methods approach, or at least trying to, here. Which is basically looking at total number of outcomes. So you got three choices for entree, three for main, and then four for dessert, giving you a total of 36 outcomes. Then I was trying to do favourable outcomes. So specifically, I was looking for getting entree, main, and dessert. That would mean 2 choices end in entree, 3 end in main, and 3 end in dessert, giving you a total of 18. That's what we had at the beginning, probability of a half for all outcomes, for all courses rather. The reason why this doesn't quite work is because we need to decrement the possibilities of what is it specifically? You've got to decrement the double omit, I think, which is what I wasn't catching on to. Is that quite right? Decrement the double omit. There are, if we think about double omitting, it was 1 choice here, so 3, and then another 3 on top of that, so 9. No, it's just decrement 3. So 18 minus 3. Yeah, okay, that's what it is. So now that I'm a bit clearer on that, the counting methods approach was basically you start with your total number of possible outcomes. That's just multiplying each of the choices at each given stage. Then you find favourable. Now, from there, once you have favourable, which in this case was... Oh, whoops, keep forgetting I've got it on the phone. Favourable was getting entree, main, and dessert. From there, you've got to make sure you decrement the possibility of omitting both. Now, omitting both was just if you choose omit on the first stage, that's like, you know, it's assumed you choose omit because we're trying to decrement the omit. From there, that first omit has 3 mains branches that are associated with it, so 3 choices are being decremented, and from then you actually only choose there's only one final choice after that, which is to omit again, because we're trying to subtract the double omit. So with that in mind, it's 1 by 3 by 3, and you decrement that from your favourable, thus giving you the 15 over 36, or 5 out of 12 that is present in the book. That one's real tough to think about. Was that at all clear why we did it that way? Yeah, that's a tough one. I think I have do I have answers for these? Maybe not. Maybe that's something I should do. If I don't already have these answers, this might be a good thing to write up a guide on. If you guys would want that, let me know. I'm happy to write those up. Otherwise, that will be the end of this class. So, enjoy the rest of your day.